Okay, so here's the 5-7 video, and let me just tell you why, like where all this is going. So 5-3, which this is the old 5-3, it's now going to be, this will be 5-8. Okay, this is the old 5-3. And 5-7, the video that you're on now, is understanding where these very complicated looking formulas come from. And when you understand where they come from, it's not as bad. And also, guys, when you watch the 5-8 video, which is the old 5-3, I would maybe go like this. Maybe not, I don't know. Okay, just so you can see like kind of what's inside of what a little bit better. Okay, so in the video today when I do the formula, I'm going to be using these brackets and parentheses. And okay, so I think that you should change your packet to that. Okay, but I mean, it's up to you. Okay, so now on to 5-7. So we're talking about the limit definition of a definite integral. And a definite integral is something that looks like this. And all it means is that the exact area under the curve, f of x, on the interval a to b. There is something called an indefinite integral, which we won't do for a little while, which looks very much the same, except you leave off the endpoints, and it means something completely different. Okay, so these two things, even though they look alike, they mean something completely different. Okay, so I'm just going to be like narrating through my notes. Alrighty, so right here we have an estimation for the area under the curve f of x on the interval 2 to 10. It is divided into two subintervals. This length is delta x. This length is delta x. The very first endpoint is called x sub 0. And then the next endpoint is called x sub 1. And here, since there's only two intervals, the last endpoint is called x sub 2. And we're not, okay, so just a little note here. Delta x, in this case, is going to be the entire length of the interval, which is 10 minus 2 because it's 8 units between them, divided by how many subintervals, so 2. So this is 8 over 2, which is 4. So delta x is really just a length of 4 here. All right. And then, okay, so x sub 0, and this is all going somewhere, guys, so just try to understand everything I'm saying, and then you'll see how it ties together. So x sub 0 is 2, x sub 1, okay, so this is, I'll call this the x value sequence, okay? And you should take notes with me. So the x value sequence goes like this. X sub 0 is 2, x sub 1 is 2 plus 1 delta x. So this x sub 1, to get to it, you take 2, and then you add 1 delta x. So x sub 2 is 2, which was the initial endpoint, plus 1, 2 delta x's. Now, the first rectangle area is f of 2, since we're using the left endpoints for the height. This height is f of 2. All right, so that's the height. And then delta, for this first rectangle, delta x is the base. Okay? And then if you want to write this, oh, okay, all right. And then I can express this as f of, so 2, I can express as 2 plus k minus 1, bear with me, delta x. Okay, so 2, I can express as this expression for k equal to 1. If you plug 1 in for k, you just get 0, so there'd be 0 delta x's. Okay, there'd be 0 delta x's. Okay, the second rectangle's area is f of this x sub 1, but x sub 1 is 2 plus 1 delta x. Okay, and 2 plus 1 delta x we can express as the same expression for k equals 2. All right, so the Riemann sum, okay, so basically, guys, you take, so this expression can represent both of these inputs, but for different values of k. Okay, if you plug in 1 for k, you end up with just 2. If you plug in 2 for k, you end up with just that. All right, so we have the same expression to represent these inputs. And what this means, this is called a Riemann sum. This is I don't know if you've ever seen this before. That right there, this is a Greek letter. It's a sigma. And in math, it means a sum. Okay, it's like a short way of writing, of saying a sum. And what this means here, okay, so see, so this expression, okay, this expression here, I just put like inside of the sigma, and what it means is you take the k equals 1 value plus the k equals 2 value. Okay, so we start at k equals 1 and you go up to k equals 2. Maybe I should put a k equals 2 up there. So from k equals 1 to k equals 2, you add these up. Okay, now let's look at another one. Okay, the same type of example, except I've taken like the same graph and I've divided it now into 4 subintervals. So this is a more, if you add up these 4 rectangles, it's a more accurate estimation of the area under the curve there. And so let's just say delta x is equal to this time 10 minus 2, that minus that, but divided by 4. Okay, so really each of these delta x's is an increment of 2. All right, so same as before, we have this x value sequence. So x sub 0 is 2, just like before. X sub 1 is 2 plus 1 delta x. X sub 2 is 2 plus 2 delta x's. X sub 3 is 2 plus 1, 2, 3 delta x's. And x sub 4, which is 10, is 2 plus 1, 2, 3, 4 delta x's. And guys, the observation that we should be making is that, so the subscript there is the same as what you, is the same as the multiple of delta x that you're adding on. Okay? Now, very similar to before, rectangle 1 area is f of 2 times 1 delta x, which you can express as this with the understanding that k is 1. Rectangle 2 area is this, which you can express as the same expression, but where k is 2. The third one, same expression, all right? So you've got like all of these identical expressions, okay? But they're different values when you plug in a different k value. If you plug in k equals 1, you get that. K equals 2, you get that. K equals 3, you get that. K equals 4, you get that. And then if you want to add all of these rectangle areas up, you just do a summation sign. So this means the sum of all of these, where k takes on values 1 through 4. Where k takes on values 1 through 4. So this is what you get. So the k equals 1 value plus k equals 2 value plus k equals 3 value. Okay. Alrighty. Now, the following two examples mimic what you will be asked to do in the problem set. Okay, so now this brings us to what you're going to be asked to do in the problem set. And darn it, my computer's about to die, and that will be horrible if it does. I think I need a new computer. Okay, give me just a second. Does that work? Yes, okay. All right, yep, finally plugged in. Alrighty, so the following two examples mimic what you will be asked to do in problem set 5-7. So just follow me, and then you're going to do 4 just like this for problem set 5-7. And remember, the goal of all of this development that I'm doing in 5-7 is for you to understand where these two formulas come from. Alrighty, so, okay, so the first thing you're going to be asked to do is draw a representative rectangle for a left endpoint Riemann sum with n subintervals. A Riemann sum is just a rectangle sum that is used to approximate a certain area. So since we're using n subintervals, when we used 2 subintervals, so the first endpoint is always x sub 0, and then the last endpoint is always x sub however many intervals you're using. Okay, so that's why for this part, you know, x sub 0 was 2, but 10 was x sub 4 because we were using 4 subintervals. So if we're using n subintervals, this is x sub 0, and this is x sub n, all right? And now the area that we want to estimate, that we want to use rectangles to estimate, is this area here. So they want you to draw a representative rectangle for a left endpoint Riemann sum. So this is how you do it, guys. You go like this. You go, okay, like right about here, like a little more than halfway. I'll call this x sub k. And k is any integer between 0 and n. Okay? And then, so if this is x sub k, all right, and let's say that this is delta x right there. If that's x sub k, then the one before it is x sub k minus 1. And think about that, and if it doesn't make sense, ask a friend or ask me. Like if this was x sub 4, we'd want this to be x sub 3. If this was x sub 12, this would be x sub 11. So to get to the previous endpoint of this interval, we need to just subtract 1. All right, so that's the idea. Okay, so we've got, so these are the endpoints of this rectangle we're about to draw. They want us to use a left endpoint Riemann sum. So that means you take the left endpoint, go up to the graph, and then that is the height. Oh, that looks bad. That's the height of your rectangle. Okay, now this height is the function value. So that the height is f of x sub k minus 1. All right, that's the height. Okay, so we drew that representative rectangle. Now, step 2, write out an endpoint sequence for the Riemann sum. All right, so we just did one rectangle, but really there's n rectangles within here. But I don't know what n is. So there's n rectangles within here. So number 2, all right, and I know this is complicated, guys, but really keep pausing the video trying to understand every step, because if you understand every step, then you'll really understand where those complicated formulas come from. Okay, the endpoint sequence goes like this. So x sub 0 is always the leftmost endpoint. X sub 1. X sub 1, look at your previous examples. Like x sub 1, you get by taking the first endpoint and adding 1 change in x. X sub 2 by adding 2 changes in x. X sub 3 by 3 changes of x. So let's just do the first three. The first three of these. All right, dot, dot, dot. And then you keep going until you reach x sub k minus 1. X sub k minus 1. And if you follow the pattern, the subscript is always the multiple of delta x. All right, and we'll go all the way up to x sub k. Okay, guys, we're doing it. Okay, now number 3, write an expression for the area of the representative rectangle using delta x. So this is 3. So the area of this rectangle, usually we write area as base times height, but it really doesn't matter the order of multiplication. So we're going to go height times base, because that's how it always appears in the formula that we're trying to understand. So the height is f of, now, okay, we want to write it using delta x's wherever we can. So f of, okay, so x sub k minus 1, if you look at your sequence, this is f, or I'm sorry, that is x sub k minus 1. Okay, so this input is the same as that input. So this is what I'm going to input here. 3 plus k minus 1 times delta x times delta x. This is the height, that's that, and then this is the base. Okay? Step 4. Right? Yeah. Express delta x in terms of n. Delta x, guys, this is why for these previous two I said note. Delta x is the length of the interval divided by how many subintervals, okay? Length of the interval divided by how many subintervals. Here they said n subintervals. So it's the length of the interval, which you always get by doing, you know, the last number minus the first number. Okay, so 14. So really, delta x is 14 over n. So step 5, write an expression for the area of the representative rectangle now using n. So wherever we saw the delta x, we're going to put that in. So area equals f of 3 plus. Now I'm going to multiply. If you don't understand this next step, then just stop and think about it. So I'm multiplying k minus 1 times 14 over n. So I'm just going to put the 14 out in front. Okay, just like that. Times. Alrighty. Now, step 6, express the left endpoint Riemann sum in sigma notation. So, this is 6. So we're going to do a sum of all of these areas. Okay, a sum of all of these areas where k takes on values 1 up to n. Okay, where k takes on values 1 up to n. Okay, here it was 1 up to 4. Here it was 1 up to 2. And if you don't understand what I'm saying now, guys, Just push through and then go back and try to process it. Okay, I know that it's a lot. Okay, and then you're adding up these expressions where k is 1, k is 2, k is 3, k is 4. So all these different, so 1, 2, 3, 4, 5, 6, all the way up to n go in for k separately, and then you add those things up. F 3 plus 14, k minus 1. I'm like out of breath because I'm trying to do this before you guys start class, which is in 10 minutes. Okay, now finally, use a limit. This is the punchline. Use a limit to express this. This means the exact area under f of x from x equals 3 to x equals 17. Exact area. Right now, guys, this is an approximate area, okay, where you're using n rectangles. And the way that you get the exact area, and this is the beauty of calculus, everything is connected, is by doing a limit. Instead of having n subintervals, we want infinite subintervals. So for exact area, we do this limit. Okay, n approaches infinity. And if n is infinity, then what you end up with, now obviously I can't draw infinitely many rectangles, but let me just give a little visual. So instead of having n rectangles, you have infinitely, when n goes to infinity, you have infinitely many rectangles. I'm doing my best. And then that gives you the exact area. So for 7, the exact area, this is notation for the exact area. It is the limit as n approaches infinity of this sum, okay? So n is going to infinity. N is going to infinity. And guys, if n is going to infinity, delta x is going to 0. If this is getting huge, delta x, which is the length of the base of the rectangle, is going to 0, because those are very, very small, like infinitely small base rectangles. Okay. K equals 1 up to n. They usually don't say k equals n. It just goes k equals 1 all the way up to n. But it's just implied that that's something you're plugging in for k. Can I do it? Oh, we have like 8 minutes. Boom. Okay. Now, let me do another example, because you're also going to be asked to do, let's do a right endpoint example. I'm going to rush, so pause the video, slow it down. Draw a representative rectangle for a right endpoint Riemann sum. Okay, so again, with n subintervals, x sub n. Okay, and then x sub k minus 1, x sub k. All right, this is delta x. This time you're using the right endpoint to go up to the graph, and that's your height. Okay. Step 1. Step 2, write out an endpoint sequence. This is the same as before. So x sub 0 is 3, x sub 1 is 3 plus 1 delta x sub 2 is 3 plus 2 delta x sub 3 is 3 plus 3 delta x dot dot dot. X sub k minus 1 equals 3 plus k minus 1 delta x. k delta x. Okay, then you write an expression for the area. Now the height is f of x sub k, but we want to use deltas whenever we can, and x sub k is 3 plus k delta x. So the height, so area, the height is f of 3 plus k delta x times the base is delta x. Step 4, what is delta x? Delta x is 17 minus 3 over n, because we have n subintervals. 14 over n. Step 5, write the area again using, replacing delta x, so that's 14k over n. If that doesn't make sense, what I just did, you've got to pause until you get it, and then move on. That's how you want to be watching these videos. If you don't get something, you pause, and then once you get it, you move on, because everything builds. And then you've got to add all these up. So these are the areas of all of the rectangles, all of the n rectangles, but for different values of k. So yeah, so for the first rectangle, okay, so yeah, all right, anyway, yeah, so just, refer back to, like, this. So this is what the, this is, yeah, okay, I'm losing my mind. So I go like this, from k equals 1 all the way up to n. So you're adding up the areas of n rectangles, okay? But n rectangles is only giving us an approximation unless n is infinity. So we do the limit as n approaches infinity. And if you guys take Calc 2, they'll probably just put infinity up there, but that comes, that's like later notation. And then these just go inside. F of 3 plus 14k over n. Okay, so guys, the only difference, duh. And when I let n go to infinity, that means that we have infinitely many rectangles. Infinitely many rectangles. And if we have infinitely many rectangles, then delta x is approaching 0. Okay, and then this is the exact area. So we did it. And yeah, so guys, you're just going to do 4 of these for the problem set. It's just so you really get the concept down. And then in the future, you don't have to go through this process again. This process is just so it makes sense in your brain why those formulas that we're doing next video work. And if you understand the way they work, then it's hard to forget them. Okay, yeah, last year, I mean, I'm going to say this to you in class anyway, but last year I just jumped right into memorizing the formulas, and it was very difficult for them to memorize them because they made no sense. It was just a bunch of weird symbols. All right, I'll talk to you later.